This is the fourth lecture of the fourth week, and we're going to cover control variables. Let's go back to our original policy question of trying to understand the relationship between class size and test score. In this problem, we're trying to estimate the effect of student-to-teacher ratio on test score, holding all the other factors constant. And in some of the factors that we have considered were share of English learners and family income of students in the district. So in this problem, the effect of STR on test score, or STR, is actually the variable of interest because this is the main effect that we're interested in. We're interested in how much the test score changes when student-to-teacher ratio changes. If we were able to run an experiment where we assign randomly different student-to-teacher ratio to each school district. So for instance, for school district 1, we assign 10 students to each teacher, and for school district 2, we assign 30 students to for each teacher. Then in this case, the student-teacher ratio will not be correlated with whatever is in UI. And since student-to-teacher ratio is not correlated with the UI, then in this case, the expectation of x given u is equal to 0. And we said that the estimated beta hat 1 is unbiased and its causal effect of student-to-teacher ratio on test score. However, this is not possible in real life. In real life, you cannot just randomly assign student-to-teacher ratio to districts, so we have to use an observational data. And in this case, student-to-teacher ratio is most likely to be correlated with UI. One of the UI example that we have used before is a family income in the school district. So if the family income of the school district is higher, then it's likely that student-to-teacher ratio is probably lower. And if the family income of the school district is lower, then it's probably likely that student-to-teacher ratio is higher. So in this case, the STR, our variable of interest, and the unobservable factor UI are correlated. In previous lecture, when we talk about the omitted variable bias, we said that omitted variable bias occurs when two conditions are met. The first is that the omitted factor, sum z, is correlated with one of the main variable of interest, in this case, student-to-teacher ratio, and if the omitted variable is affecting the test score. So in this case, we have a omitted variable bias. And when you have an omitted variable bias, the main coefficient, beta hat 1, would be biased and it will no longer be causal. So in the previous lecture, we said when there's an omitted variable bias, one of the solutions is to include that omitted variable. So in the previous case, we said that percent of English learner is correlated with student-teacher ratio and has a direct impact on test score. And hence, if it's omitted, then it will cause an omitted variable bias. So we can include this variable and solve the omitted variable bias problem. But there are other factors that may not be observed, and we cannot easily include it in the regression. One of the examples is parental involvement in children's homework. So how much parents are involved in helping children with their schoolwork. So that parental involvement has a direct impact on test score, but it's probably also correlated with the student-to-teacher ratio. However, the problem is that you cannot directly observe how much parents are involved in children's schoolwork. But we also know that this parental involvement is probably correlated with family income. The assumption is that parents who are higher income is also more likely to be involved in children's schoolwork. So you can include something like this: percent of students receiving a reduced price lunch. Since only students who come from lower income families receive reduced price lunch, this variable is sort of an indicator for family income, and hence it's probably correlated with parental involvement. We call this variable control variable. So control variable W is a variable that is correlated with and controls for an omitted causal factor in the regression of y on x, but which itself does not necessarily have a causal effect on y. We said previously that student-to-teacher ratio is our variable of interest. In this regression, the percent of English learner in the school district is a control variable. This control variable, percent English learner, can also have a direct causal effect on test score. Because when you have a high percentage of students in the district who is learning English, then it may actually lower the test score because it's tough to take a test in English when your first language is not English. So the percentage of students who are on reduced price lunch program is also considered a control variable. But unlike the percentage of English learners, which had a causal interpretation, this does not have a causal interpretation. As you can see, the coefficient for the variable for percentage of students who are enrolled in reduced price lunch program is negative, meaning that when there's a higher percentage of students who are enrolled in reduced price lunch program, the test score is lower and vice versa. But this does not mean that one causes the other. If one were to cause the other, so if somehow the percentage of students who are enrolled in reduced price lunch program affects the test score, then someone may try to increase the test score by getting rid of the reduced price lunch program and making this variable equal to 0. But we know that just getting rid of the reduced price lunch program is not going to increase the test score. And that means that this variable is not causal. In short, control variables doesn't always have a causal implication or causal interpretation. So there are 3 interchangeable statements about what makes an effective control variable. So an effective control variable is one which, when included in the regression, makes an error term, in this case ui, uncorrelated with the variable of interest, in our case, the student-to-teacher ratio. So in other words, once the control variables are included, then the error term and the variable of interest are no longer correlated. Another way of saying this is that holding constant the control variables, so in our case, our percent English learners and percent of students who are on reduced price lunch, the variable of interest is as if randomly assigned. So controlling for the control variables, the student-to-teacher ratio is as if they're randomly assigned across the districts. Another way of saying this is that among individuals with the same value of control variables, the variable of interest is uncorrelated with UI. So they're all saying the same thing, and in mathematical term, we call this conditional mean independence. So if the conditional mean independence in the previous slide is met, and in addition to that, if the other least square assumptions are satisfied, so the second assumption on IID, the third assumption on having no outliers, and the fourth assumption on having no multicollinearity, then we know that the beta 1 has a causal interpretation and it's also unbiased. We don't know if the beta hat 2 or the coefficient on control variable will be biased or not, but we really don't care about that because what we really care about is beta 1. And as long as the beta 1 has a causal interpretation and it's unbiased, we are satisfied.